Let's take a look at a couple of examples of using Newton's second law. Before we begin our examples, let's first determine what is mass and how is it any different from weight? Say you had a pile of bricks and a pile of feathers. Which one has more mass? Which one weighs more? Well, one standard red brick is an average of 2.27 kilograms, whereas a single feather is less than 1/100th of a gram. So in terms of mass, the pile of bricks will have more mass than the pile of feathers. But what about their weight? So before we can answer this question, let's get the definition of mass first. Mass is a measure of how much stuff, how much matter is in an object. The number of atoms and how densely packed they are within a certain object determines its mass. Weight, on the other hand, is a measure of gravity's effect on that mass. So gravity pulls on the object, which makes massive objects heavier and more difficult to lift than less massive objects. The mass of an object will never change. Your mass will never change. You have a certain weight on Earth because of Earth's gravity pulling on you. But if you travel to the moon, you will weigh less. Gravity is weaker on the moon than it is on Earth, so the gravitational pull of the moon on you will be less than the gravitational pull of the Earth on you. So you'll weigh less on the moon. It's not an ideal way exactly to lose weight, but the concept is definitely there. So going back to the pile of bricks and feathers, if they both weighed 1,000 pounds, that's because there are enough feathers to account for the same amount of mass in bricks for the two piles to actually weigh the same. In the first example, we'll have to find how fast a 0.60 kilogram box will accelerate if it is given a 13 Newton push. Now, 0.60 kilograms is 600 grams, or just a little under 1.5 pounds, like a typical bottle of water. And to get a sense of how much force 13 newtons is, think about how hard you can bite into an apple. That type of bite is typically about 300 newtons of force, just due to your incisors. So a 13 Newton push might be like a light tap in comparison. So let's start with Newton's second law, F equals ma. F is 13 newtons, m is 0.60 kilograms, so we get 13 newtons equals 0.60 kilograms times the acceleration a. To isolate a, we divide both sides of the equation by 0.60 kilograms, which cancels out on the right side of the equation. Now a equals 13 newtons divided by 0.60 kilograms, which when we do the calculation is about 21.667 meters per second squared. But we need to round off to two significant figures because of these two numbers in our original problem. So we cut off our answer right after the second digit, and we rounded up because of the 6 that follows our cutoff point. So our final answer, when we rounded it up to two significant figures, is 22 meters per second squared. In our next example, we need to determine how much force is needed to move a 258-gram rock, which is probably really a pebble, with an acceleration of 45 meters per second squared. So again, we start with Newton's second law. However, we have to remember that the mass in this equation must be in units of kilograms. So our 258-gram rock will actually be 0.258 kilograms, which gives us F equals 0.258 kilograms times 45 meters per second squared. Multiplying these two numbers together gives us 11.61 newtons. And again, we have to round our answer to the proper amount of significant figures, so we look back to the original problem. But notice here that we have one number with 3 significant figures and another with 2. Our answer will always have as many significant figures as the number in the original problem with the smallest amount of significant figures. So in this case, that means 2. So again, we cut off our answer after the second digit and round it up because of the 6 that follows after that cutoff point. So our final answer, rounded to two significant figures, is 12 newtons. In the last example, we'll determine the mass of a boulder that is accelerated by 0.17 meters per second squared if it's pushed with a force of 4,000 newtons, assuming that one person could apply that much force. We can of course anticipate this boulder to be extremely massive if it gained such a small amount of acceleration after such a large force was applied. So let's start solving by bringing in F equals ma. Now, the force of 4,000 newtons will replace the F in the equation, and A will be replaced by 0.17 meters per second squared. But the M remains as so, since that's what we're looking for. So we divide both sides of the equation by 0.17 meters per second squared to isolate the M, and we get those two terms canceling out. And M is equal to 23,529.41176 kilograms. That's a whole heap of kilograms. But again, we have to round off our answer to the proper amount of significant figures. And in this problem, the two numbers we were given have either 1 or 2 significant figures. We go with the smallest amount and determine that we must round off our answer after the first digit. So looking at the 3 that follows our cutoff point, we round down to 20,000 kilograms to maintain the same order of magnitude in the tens of thousands as the original answer. But now we also have the right amount of significant figures too. Now, 20,000 kilograms is also 20 kilograms. Though we don't generally use this term as a unit of mass, we could also say that this boulder's mass is 20 megagrams, since a kilo, or 1,000,000, is the same thing as 1 mega, or a million.